Like I said, it's not what my channel is going to be about. But this is for a couple relatives of mine. I'd like to just put it up basically for them. If someone else wants to look at it, that's great. Anyways, basically, I'm just going over a couple weird physics type things. Um, Five main rules I'm going to talk about here first, or one, as you can see up there. There is no way to tell experimentally if you are moving or standing still. And basically, everything in the universe, nothing is moving and nothing is standing still. Everything is only relative to another thing, which is the second rule there. Things only move relative to each other. Um, Number three, light moves at the same speed no matter what frame of reference you are in. All frame of references are equally valid, and the faster something goes, the slower its clock moves, the shorter its length gets, and its relative mass gets greater. Um, I'll talk about that first thing. I want to first explain what frame of reference is. I'm going to give you some examples because that's basically the easiest way to know what it is. If you look here on the picture here with the train, right? The first train, the guy, the little dots there, that's a ball. He throws the ball up and it goes through these um, five spots and it comes back down to those five spots. And as you know, if you're on a train and you're moving at exactly the same speed, no bumps or anything, you throw a ball up, you can't tell that you're in a train. Okay. But what about a guy who's standing outside the train, right? He sees the train moving and the ball moving. When you throw the ball up, by the time it gets to this second dot, the train has moved over. By the time it gets to the third dot, the train has moved even more, and so on and so forth. So this guy outside the train, he's a different frame of reference. From the frame of reference of the train, the ball goes up and down in a straight line. In the frame of reference of a person on Earth, not on the train, the ball goes in an arc type palabra shape. Okay. They're both equally right. Okay. And you could say, no, they're not equally right because I know that the guy in the train is moving. When I'm on Earth, I'm not moving. So obviously I am right. It's a palabra, it's a arc. But if you think about it, okay, you only think that because you only live in one frame of reference. And your frame of reference is usually from Earth. When we say, your car goes 50 miles an hour, we don't say it goes 50 miles an hour relative to Earth. We just assume that. It's already ingrained in our thinking. But I want you to think about, look at this little guy here. I know it's a terrible picture, but that's supposed to be a spaceship, and he's in outer space, um, just standing still looking at the Earth. Okay. What does he see? He doesn't see a line. He doesn't see a palabra because the Earth is spinning. And not only is it spinning, it's moving around we'll just say that he's hovering above geosynchronous. So he sees that arc also spinning around the planet. So it's not an arc anymore to him. Now, what about a guy on the sun? You could say, well, the spaceship's in is the correct answer. But what about someone on the sun? Now, not only is the Earth spinning, not only is the train moving, the Earth is spinning and it's rotating around the sun. So, from his perspective or his frame of reference, it's neither of the first three that we said. You can say, well, that it must be his frame of reference that's the correct answer. But if you think about it, what about a guy who's not inside the galaxy, but he's hovering above the galaxy, looking down on us? Not only is the train moving, the Earth is spinning, the Earth is going around the sun is going around the galaxy. And not only that, if you move on to the next frame of reference, the entire galaxy is moving through space. So no matter where you go, there's always going to be a different frame of reference from yours. And the thing you need to understand is that each frame of reference is equally valid. Meaning, when this guy on the train says that his ball goes straight up and down, that's true. It does go straight up and down. Okay? Because there is no frame of reference that is wrong. They're all correct. And if you think about it, if you have two guys sitting out in space and they're in spaceships, right? And all they can see is out their little window to the other spaceship. The other spaceship blocks the rest of the view. All they could see is each other. Okay. How do they know which one is moving and which one, I mean, if they're moving or not? You know what I mean? If they pass each other in space and there's nothing else to look around and say, he's moving and I'm not, how do you know who's moving? You experimentally cannot tell. You cannot tell if one spaceship is sitting there while the other one's driving by, or vice versa, or they're both moving. You do not know. You cannot tell. You can only say relative to something else if something is moving. Okay? Now that's what a frame of reference is. And I want to give you a thing here, another picture here, because the frame of reference we were talking about for light is that we're saying that it moves at the same speed no matter what. That's one of our thingies here. Okay? Look at this picture here. Now I want you to think about this. You got a guy on the train. The train is moving 100 miles an hour. He throws a ball at 100 miles an hour, meaning attached to the train is one of them ball things, you know, like for baseball. It's reading 100 miles per hour. He's throwing it from the back of the train to the front of the train. So how fast is that ball going? Well, it's going, according to the guy on the train, it's going 100 miles per hour. And he is correct because every frame of reference is equally valid. But what about this guy who's standing here and he's watching the train move? Now, the train, the man, and the ball are all moving at 200 or 100 mile an hour towards this man. So if he throws the ball at another 100 miles an hour, that ball is moving 200 miles per hour relative to this guy standing here. So in one frame of reference, the ball is moving 100 miles an hour, and another one, it's moving 200. What about this guy here? He's running in this direction with the train at 10 miles per hour. So when that ball comes and it would be 200 miles per hour, but he's running another 10, so that takes it down to 190. And if he runs towards it, now not only is the ball coming at 200 miles an hour, he's going in the opposite direction at 10. They add up to 210. Now the big question is, well, then how does light? Because as you can see, in each frame of reference, the speed of the ball changes. And that's for anything. I mean, if he's throwing a kite, whatever. Two speeds always add up, or you know, they always minus or whatever. They're never the same for any other reference frame, okay? How does light? How does a guy throw a beam of light, and they all get the same speed? How does that happen? Well, I want to get into that. I want you to think of, though, what is speed? I mean, speed is distance per time, right? So if this thing's going the same speed, how can you, if it's light, the light particle or photon, how can we have it be the same in each frame of reference? Obviously, something has to change. Something is different between these two guys, and speed is defined by distance divided by time. So either their time or their distance is different between these two people, or all four. And I'm going to show you how that is possible, okay? Now, what do we have here? We have a two-dimensional graph, right? Right here, for three-dimensional space. Nobody complains when I do that. North, east. If I do that, no one bats an eye and says, hey, what about the other third dimension? I don't see that third dimension. Why isn't it on there? Okay? Now, I want you to think you're a car. Here's 0.00, right? You're not east and you're not north. You're at 0, 0. Now, let's say you move 5 units and you go directly east. Okay? 5 units, 5 miles, whatever. You're driving in a car, you go 5 miles. How far east are you going to get? You're going to get 5 miles. But what if some of your direction is diverted to the north, right? Let's say this guy here, this is 5 units here too, because as you can see, it's a circle, meaning this is a radius, this is a radius, all these are radius. This line here is a radius. That means they're all equal, right? So this is 5 units. What if he drives along that line? How much time, or I mean, how much distance did he go east? As you can see, it's like about 4 units or 4 miles, say. So if he drives east 5 units, he goes east 5 units. But if he goes 5 units and he directs some of that direction from east to north, then he's not going to go as much east, is he? Because he directed some of his direction to the other way there. Okay. Now, I want you to look at this next graph here. Okay. This is time and space. It's a two-dimensional graph for four-dimensional space-time. And you could say, well, I don't understand. I don't understand. Yes, you do. I just like over here, I didn't write the other dimensions. Okay. You got two dimensions here, north and east. You got two dimensions here, time, and you can say north. So let's have that space be north. Okay. Now, if you are going straight, if you don't move, right, and you just stand still right here at this point, right, time is still moving. You will actually be moving at the fastest that you can move through time. You cannot move through time faster than just going along this line, right? But just like over here, the fastest east you can go is if you divert all your energy going east. What if you divert some of your direction going north over here? Look at what happens. Just like here, you got your little radius. Let's say a person goes here, right? Along this arrow. Now, if he goes along that arrow, he is traveling through space and time, because you can't you're always traveling through time. But as you can see, he's diverted some of his direction in time to direction in space. And as you can see, look at the thing, how I have it going down. It's going down to, I don't know, 4 units, let's say, on there, or 4/5. So the faster you go, if you're going 0 mile an hour, you're not moving through space at all. You're going as fast as you can through time. But the faster you go, the less you're going through time. The faster, I mean, the faster you go through, like what you would consider your spatial dimensions, the slower you go through time, right? Because you're going to divert some of your energy, some of your direction. And let's say you didn't move. So here's where you're at, standing still. Okay, you can see where I'm at here, right? That's the fastest you can travel through time. Now you start moving. Now you're going 10 mile an hour. Now you're going 20 mile an hour, 100 mile, 1,000, million. Oh, not a million. And you keep going faster and faster, right? When you get to this spot right here, okay, as you keep going, time slows down. Actually slows down just for you, not for anybody else in another frame of reference. But time will slow down. If you keep going, keep going, keep going, when you get almost to the speed of light, time is almost stopped. And when you get to the speed of light, 186,000 miles per second, now you're only traveling through the spatial direction. Look at where you're at on the timeline, though. There is no time then. Time will stop at the speed of light. And I'll explain more about that later, because I'm running out of time here. So I think I'm going to have to call it or whatever. But like I was saying, if you went through space at the speed of light, time is right here, 0. And if you go through time and you don't go through space, you're going the fastest you can go through time. But if you keep putting in some speed, you want to move your direction in space also, then you're going to slow down time. And that's how you can have light moving at the same speed for every frame of reference. Anyway, this is John Black, and I'll try to get back with you another movie. This is the first one, and like I said, this is not my, this is something just for basically a couple people. But if anyone wants to put some, I love talking about physics, you want to post something, post it. Let me know what you think. All right, bye-bye.